I'm going to base the final exam, which is going to be 2 weeks, on the following problems. And so this is going to be the review problems. Okay. I guess I'll just list them in chronological order by section. 5.9 AB, C is extra. This is again one of those, it's a lot like 511, which didn't work out so well. I'm going to try another one because he has another one in there. This time he actually reports in the data the standard deviation, so you don't have to compute them. It makes it a little bit nicer. And just try to do the weighted least squares again for parts A and B, and see what you can do with part C if you want to. Okay. 710 is just kind of a white book problem. It has nothing. It has to do with, do you understand what a spline is? Okay. 720 is as a quadratic fit, which is not a tough problem, but it's a good review problem. And let's see, 8.5, a little. You have to use some indicator variables in that one. Actually, just one indicator variable. It's pretty much just like the lathe speed exercise. So that's kind of not that difficult. 9.4 is your homework that's due on Thursday, which is going to be the forward and backward and stepwise regression, all possible regressions kind of a thing. I don't know how I'll make a problem on that, but I'll figure something out. Okay. And then I'm going to have one more problem, 12.8. That's what we're going to do this week. We're going to do nonlinear regression. Okay? It's not that difficult. And there's more I can certainly do than that. And if there's still extra time, well, I guess I'll just relegate it to extra credit. Okay. Okay? So this is like a makeup problem because you didn't do that other homework problem. Easy, your homework. Not that easy, but that's what we're going to learn that week. Okay? Okay. So that's the final exam paper. I'm not going to, you can turn it in with your exam, but I think I'm pretty much just going to base the exam on the exam day. I'll take the papers you have as, work toward the exam, like to explain what you were doing in case you were having difficulty or something. Okay? Is everybody okay with that? You don't have to turn anything in.
So then how's that help you?
How's it going to help you? Only help explain what you did. If you ran out of time or something like that. It's not going to help otherwise. It's just the way I'm going to do it. Because I decided no more take-homes. Okay? Yeah.
So we can do those and understand everything about those. That should be all you need for the final thing.
Yeah, you can ask questions about these at any time between now and then. Unfortunately, you won't be able to get a hold of me next week, okay, because I'll be gone. But on Monday when we come in here, you can drill me on all this stuff, okay, before the exam, okay? Up to a point. I'm not going to spend 2.5 hours doing it because then we'll run out of time. But, we can save 45 minutes or half an hour for that. That won't be televised, obviously. Okay? This is the last week of the camera. Okay? So, yes?
Is it going to be similar to like the quiz you gave?
Kind of, but it's going to be longer. And I'm going to try to... That quiz, I think, was a little bit easy. Okay? But I'm going to do similar type of things. Do you understand how to, what to do in these problems? I'll try to give you a little bit more indication, but... I'll be putting printouts of, correct solutions, what I thought were correct solutions to the problems, pieces of the problem, and saying, refer to this piece, refer to that piece. Okay. Do you understand what's going on here? And I have plenty of, all these problems have examples with them. We can go over another problem like 5.9 if you want to. Okay, but we had a little bit of trouble with 5.11. I can bring that back out on Thursday and talk about it. Okay.
Will it be open book as far as for this one?
Yeah, I'll just go ahead and let you have the book. But I warn you about that because I've taken an exam open books. Oh, this is a piece of cake will come in here. It killed me. All right, it's the only course I ever got a B in baby graduate school because it was open book, and I actually thought, that did not work. Okay, so I warn you ahead of an exam. All right, on that. So yeah, like the quiz, longer. You got to do these problems, obviously. Okay, so there's 2 problems that you haven't done yet at all, and well, maybe 3. Okay, they haven't even studied that much. Okay.
It says you'd have the solutions to the other ones.
I have all the stuff that's on the website is not on the website. I'm not going to give the solutions to any of these.
Right.
All the other problems you've done, only what's on the website. I'm not giving all the solutions to all the homework problems. So, 9.4 is going to be due on Thursday, so quiz me down about it. We're going to go over that today. Anyway, we're going to go over regressions, all possible regressions and whatnot.
And it's just
The same time, 10:50. I don't know. I still haven't constructed what it's going to actually look like to make it look like the quiz we already had. It's not that easy of a job. I'd rather not have to do that. But I guess that's life, Okay? So I'll figure out a way. You all seem to handle that pretty well. Okay. Other comments about the quiz / exam? But I decided that's going to count half. It's not going to make any difference, I don't think, in almost anybody's case, that was half and the take-home was half. So if that's true, then the final exam should not make a big difference either. Okay? It's just, do you know the stuff, that you did there? Okay. So I think it'll be fine. It's a method. It's just a little bit difficult for me to have to deal with. That's all. So why don't we get started on some... I have some Minitab output. If you don't have Minitab, we're not assuming that you know how to use Minitab, but it doesn't really matter because this is going to be an all possible regressions formula. When it comes to the exam, I'm not going to assume that you know anything about this sheet per se. This is more conceptual, okay? I mean, the form in which it's put out. The actual theory inside, of course. The way it's laid out is just more efficient than Excel will be able to do, because Excel won't be able to do it this way, right? So when I actually make the exam, I'm going to have to go the long, hard way when it comes to this kind of problem in terms of putting out page after page of output. Okay. Well, not page after page, but, not going to be quite as nice and compact as this. I will give you only refer to Excel worksheets when I give the final exam. Okay, no other software will be referred to. But I thought this was just such a good example of how to do forward and stepwise regression and so on that I would just show you how to do that. So this is not going to be on the website because I don't actually have a soft copy of it. Is that okay? So I have some slides of it though, so maybe I'll put those up and we can get it at least archived or something like that. Okay. So I could probably come up with a soft copy version of it, but since you all don't have Minitab, what's the point? Okay. We used to use Minitab here. Yeah. Minitab and Excel, yeah. Minitab is pretty common. Excel is obviously the most widely available since it's free, practically speaking.
So what are we going to do? We're going to look at the property valuation data, the house price data that you had to study for your influence analysis. I didn't put any of that influence analysis on the exam, okay, as you saw. I could change my mind about that, but right now I'm not planning to, okay? So what do I have here? This is kind of small script. But what I'm looking at is Minitab, what I have to do to tell it to do some work. This is problem 9.6 actually from your text. Okay. If you want to read it. It just says take the house price data and consider that data. Use all possible regressions method to find the best set of regressors. Use stepwise regression to select a subset regression model. Does this model agree with one found in part A? Well, it depends what the best set of regressors is. What's your criterion? I'm not going to actually do all possible regressions. How many regressions is that? 2 to the 9th. That's 500 and, 512 regressions. I'm not going to do that, okay? But, so I'm going to do a lot less computation and come up with basically the answer. Okay? So what we have here is regress the price on 9 variables. That's the 9 here. That says you're going to have 9 regressors in the syntax of Minitab. Okay. And those are the names of them. I apparently had named the regressors. Okay? In the worksheet that doesn't show here. Okay. So now the regression equation is this. It just gives you what the regression equation is. Multiple linear regression. Okay. And then here's the coefficient, standard errors. They call it standard deviation, but that's what we call it, SE. Okay? T ratios and p-value. They call the p-value p, but I'm going to use p for something else because p is going to be the number of columns in a reduced model X matrix. Right? So what the heck is this? Well, first, I'm not going to derive CP yet. I'll talk about CP a little bit later. But what is CP? CP is, let's just go ahead and apply it first, and then we'll go see what the heck it is. Okay. CP is the residual sum of squares when I use a subset model. Just use a subset model, and this is notation for it, SS res of P. Okay. That's the residual sum of squares in a subset model. And then I'm dividing by the full model estimate of variance, which means SS res full, okay, divided by n minus k plus 1. This is the full number of columns in the full model. Number of columns in the full model X matrix. So what is sigma hat squared full? I guess I should say what that is. Sigma hat squared full is then SS res full divided by n minus capital K minus 1. The notation in our book is a capital K is the number of regressors. Here, 9. Capital K plus 1 is 10. Because you have 10 parameters. Intercept plus the coefficients, the slope coefficients of the 9 regressors. Okay. So capital K plus 1 is 10. Corresponding to 10 parameters. All right. So this is just n minus 10 down here. Okay. What is n in the house price data? There were 24 degrees of freedom. The Minitab does give you the ANOVA output, but somehow I erased it because it was taking too much space on this slide. And I just stuck in the Excel ANOVA table there in smaller font. Okay? On this cut and paste deal here. Okay? So there's the ANOVA table. The actual number of observations in the house price data was 24. So n is 24. Where did I stick that? N was 24 in this problem. Okay? Well, n was 24. Okay? In this problem, n is 24. In and capital K plus 1 is 10. All right, so what I did is take the SS res full, which is this, 121.7, right? And divide it by 14. This is the usual thing. It's just this is my sigma hat squared right here, 8.696, which you had to deal with a bunch of times in your homework. Okay? So that's the 121.7 divided by 14. Okay? So you take this, so this is going to, since, what are you doing? You're getting, let's see, is this correct? Yes. If you just divided by, so you got to have the full model estimate of sigma squared here. If I just took SS res of p and divided by n minus p, which is the number of degrees of freedom in SS res p, all right, then what do we get? I would get SS res p divided by SS res p by n minus p. I would just get n minus p minus n plus 2p. I would get exactly p. Okay? So, so the idea here is that really, if your model is successful, then CP should approximately equal to P. We'll derive that a little bit later. Okay? But what you really want is for CP to be approximately P maybe, but as small as possible, actually. You want the smallest subset model, which is reasonable. Okay, so the minimum CP is sometimes taken as the criterion. That or minimum MS res P, which is just SS res P divided by n minus P. So MS res, we didn't put that in here because I don't think there's any table where actually, oh, here it is, MS res here. This is MS res full. This is MS res full. Okay, and then on the later slide, I think about the MS res P corresponding. Okay, so I want to try to make that small. I want to try to make CP small. Okay, so here the CP for the full model is simply the number of columns of the full model X matrix, the number of parameters in the full model. So P for parameter if you want. P for p-value, but this P for parameter. Okay, number of parameters. So that includes the intercept in this case. Okay, so that's just telling us what happened. That's one regression, full model regression. Okay, so and here's the general formula for CP. All right, now the test statistics. Okay, now here's something that used to be done in this book in the second edition. For some reason you took it out, but I think it's worthwhile as a teaching tool to talk about the directed search on T. Okay, let's talk about T statistics. What are these T statistics? These T ratios here. I've dotted 1.87, 1.63, and 1.46. Why did I do those? And then there was 2.52, but that's just the constant. All right, that's the biggest one, but I'm not so interested in that. Okay? The test statistic for testing H naught beta j equals 0 for the full model is this, TKJ. He's got the capital K thrown in there. He may have actually thrown this notation somewhere in this text too, but this is not so important. I just take the coefficient, divide by the standard error, which you studied way back in chapter 2, okay, and 3, and that's my T statistic. Regressors that contribute significantly to the full model after the others have all been fit, remember, will have a large T statistic and will tend to, in absolute value, and will tend to be included in a best subset model. The directed search on T, well, how large is large? The directed search on T method is to rank the regressors according to the decreasing order of these absolute values of T statistics and introduce them one at a time to determine a sequence of subset models with increasing P. That's pretty simple to illustrate. Let me just go ahead and illustrate that. So what I did is I marked taxes, BABs, and garages as the top 3 T statistics in absolute value after the constants. What I'm going to do is this direct search on T is just go ahead and add those 3 variables in one at a time in succession, adding a variable each time, not taking the other one away. right? Just accumulate a larger and larger model, okay, and just see what happens. So, directed search on T. First I put in taxes, and so now I have two coefficients. One is the intercept and one is the slope of the taxes. Okay, so my subset model is this. One regressor, and P is 2 here. Okay? So, and to not to confuse it with the other P's, I hand wrote in p-value for what the p-value is for the significance of the model. Okay? So here we have, now we look and see, yes, indeed, taxes is significant. Okay? It's the same as the significance of the model, that T ratio. Okay? They don't even bother putting the F in here. Okay, well here it is, F. That's 8.52 squared, as we know. Okay? Okay? So there's the analysis of variance table. What's the CP, though? That's what I wanted to calculate. 192.89. This is the error or residual sum of squares. I always get that messed up. Error or residual sum of squares divided by the 8.696, the sigma hat squared full, right? Minus 24, because that's the minus n, plus 2p. Remember the formula? Go back to it? Okay. Well, you can go back to it. So that is, this is the minus n plus 2p, and this is SS res p over sigma hat squared full. Okay? Minus n plus 2p, that's what it is. All right, and that comes out to 2.18. Okay, well, that's a lot smaller than 10. Okay, okay. Let's go to p equals 3 to see what happens there. So now the next one was after, let's see, in the directed search on T, I think the top T statistic in absolute value among the regressors was 1.87. The second one was 1.63. That was BAS. It's not just because these are ordered this way. You know, they just happen that way. The BAS, after all the other ones, was almost still significant. Actually, taxes wasn't after all the others at the 5% level. Taxes was not significant after all the others were fit. Okay, at the 5% level. There's so many variables here. Okay. BAS was not significant either after all the others were fit, but it had the second most significance after all the other ones. So here we put in the BAS, and now we have significance of the model, obviously, again. Taxes are still significant after BAS have been fit. BAS are almost significant at the 5% level after taxes have been fit. Okay? So this is a subset model. BAS, number of BAS, okay, and so on. CP is, 0.826. Okay. So that turns out to be the minimum. Let's see, that's 163.71 over 8.696 minus 24 plus 6. Does that make sense? Over here we had 192, so SS res dropped. Okay, not that much that it was going to make BAS significant after taxes, but enough so that the CP went down to, see, does that look right? 20 minus 24 plus 6. Maybe I made a mistake. No, that's right. Looks okay. 0.826. Okay? Now that turns out to be a minimum CP. How did I know that? Well, I didn't, because I didn't do all 512 regressions. Okay, not shown. Okay? So it would be nice to show a graph of all the CPs and so on, all the 512 dots. That'd be cute, but I don't have the computational power for that. Okay. So, let's just finish this up now. What is the forward and backward regression and so on? Maybe do one more step in the stepwise regression, see what happens. I mean, in the directed search on T. Directed search on T, I'd do one more of those, and I went to, let's say, I threw in garages. Okay? Now, strangely enough, the T statistics for BAS have gone up. Okay. That's because, remember, the error sum of squares keeps changing here to 7.88 now. Okay? For the mean square. So MS-res, I didn't show that. MS-res P here is 7.88. This is MS-res P. Okay, at P equal to 4 for this particular subset model. Okay. Versus in the previous slide, what we had was, well, I guess that was the same almost. That had a smaller MS-res too. They had a 7.80 for the MS-res. Okay? So they had a small MS-res too. Okay? Okay. So garages don't contribute hardly at all to the model. Okay? Apparently. So I put NS here, not significant. Okay. So X1, X2, X5, that model, okay. CP is 2.13. Yeah.
So do you know to stop because it went up again? The CP value instead of the, I mean, you're trying to minimize the CP, right?
Yeah.
So
Yeah, well, I mean, it went up again, so it's not as small as the other one. Yeah, I mean, in terms of directed search on T, I think I would definitely stop here. Okay, and either include X5 or not. Probably not.
Yeah.
Okay, just stay with the X1, X2 model, minimum CP. If I was going to use this method, so that's one method to find the best model. Okay, pretty simplistic. Okay. Now, what's stepwise regression now? That actually is the other method, and there's actually 3 methods discussed in the text: forward regression, backward regression, and stepwise regression. But actually, stepwise contains all 3 in a unit, as you'll see here. Okay? There's 2 parameters. Fn equals Fenter, because that's what they call it in Minitab. Okay? So there's various notations for what it's a parameter. Like an F value, like 2, 3, or 4, or something like that, or 5. Usually bigger than 1. And F out is F remove. Starting in a P subset model, stepwise considers a single regression with the largest T statistic. Oh, okay. Yeah, you have to consider all possible P plus 1 subsets. So you start with some model like P equals 1. In other words, nothing. Okay? Except the intercept. And then you have to consider all possible P plus 1 subset models. So you can consider first taxes, VAT, whatever. So that's exactly the same as the directed search on T. I'll take the one that has the largest T. All right? That's taxes. All right? Or if I had more, if I was at the X1, X2 model, okay, taxes and VAT, then I have to consider all possible 3-way subset models, okay, that included those 2, X1 and X2. So I consider X1, X2, X3, X1, X2, X4, X1, X2, X5, X1, X2, X6. You following? So this would be if, what am I saying here? Okay, I'm saying that if you start, if P equals 3 and if P equals 3 subset model consists of X1, X2, all right, then P plus 1 subset model will be one of. Okay? X1, X2, X3, X1, X2, X4, X1, X2, X5, etc. All right? I'll consider all possible things. So that would be, what, 7 of them, right?
Can we do that in T with alpha?
Well, let's see. What does it say? It says, stepwise considers a single regression with the largest TJ in the corresponding P plus 1 subset model. Okay? So that's a little bit different than directed T, because directed T started with the full model T values. Now I'm only going to consider the subset model. So here, Okay, and so single new regressor. Okay, I didn't put the word new. Okay, single new regressor. So we're talking x3, x4, x5, and so on, which is the biggest one. All right. So let's say I'm at x1, x2, minimum CP. Am I going to add anything? Okay. Well, I have to consider all possible situations. Okay. And that corresponds to, and now I'll enter that x3, x4, x5, x6, or whatever up through x9 if the f equals tj squared is bigger than f enter. This was not very clear here, but it's hard to describe. Okay. You'll see how that goes. So then we accept, and then we're going to get to this new p plus 1 subset. If the regressor in this model with the smallest, not in this new model now, so now I'm at a p plus 1 subset model. Okay? I've just, let's say, added one. Otherwise I didn't. Okay? Where the smallest partial F statistic has f less than f remove. Okay, suppose now then one of the t's in that p plus 1 subset model has t squared less than f remove, or f out. Okay? Then I take that regressor out, so I can actually take one away now. Okay? Maybe one of the ones I already had in. Okay? Then remove this regressor and go back to a p subset model. Okay? Now that's a new p subset model, presumably. Okay? Because I can't take the one that I just added in, because I just added it in, unless f remove was, unless f could be bigger than f enter and less than f remove, unless f remove was bigger, okay, then I would just take it out and I don't really keep it anyway. All right? It doesn't make sense. Okay? So it's harder to enter than it is to, you should always take f remove less than f enter. Okay? I think they mentioned that in the book somewhere. It's chapter 9. Yeah, you take f remove less than f in. F out less than f in on page 314. Okay? You might take them equal. That's okay. So I don't want to take the one that I just added in out again. That's kind of silly. Okay. Because I'm not doing a new regression to check that. I'm just checking the t squareds, okay, and see if they're bigger than f or the parameter or less than the parameter. Okay, then we go back to this will lead to a different p subset model. Therefore, one should first check for further removal of regressor before attempting to enter a new regressor. Okay, so I might actually remove a couple. Okay, I might keep going. I might throw a couple down. All right, if I was in a large, suppose I got 5 regressors in there. Then added a new one, and then I'm going to check. This one's so significant, then I have to check a couple now. Okay, doesn't make sense, but it's possible. Okay, I mean it might not make sense. By choosing f remove equals okay now, so that's the end of it. So then you get back to some p subset model where you can't remove anything more, and now you're basically starting again. Okay, now go through the iteration again. Now you're at a different p subset model. Now try to look at all p plus 1 subset models. All right, see if there's anything else to add in. Okay, anything new to add in. So is it clear now what you're supposed to do? I'll show you here the program. But now, by choosing f remove equals infinity, we obtain forward selection. That means I never take anything out. Okay, that's kind of breaks the rule that f remove should be less than f in. Okay, but that's, in other words, I never take anything out. All right? It's kind of a silly thing, but you can do it, okay, with these parameters. By starting with, and then by starting with p equals k plus 1, suppose I start at the full model and taking f enter equals infinity and never put anything back in. Okay? We obtain backward elimination. Okay. So those are the two subcases. But generally, stepwise will have f out less than F entered to get that, that kind of swiveling effect. Oh, I'll take this subset. No, I'll go back and I'll take this one and I'll go get another one. Okay? Let's see how it looks. Okay, so let's do stepwise. Page 4 of this handout. Let's try stepwise, and what did I start with? I started with what did I ask for? Oh yeah. Here basically I just put in this best one. I'm not sure what this is. This is an alternative model or something. Okay, that's a subcategory. Basically I put these parameters in and I started from square zero with no regressors in the model. Okay? So to enter anything in, it has to have the property that if I look at all possible one regressor models now, x1, so the program looks at x1, these possible subset models, just the singleton models, okay? Okay? And the one with the biggest F statistic for the model itself, which is equivalent to the T statistic for the coefficient, the T ratio is 8.52 for taxes. That was the biggest of all the single T's. If I put in only baths, I didn't do that, you can see. I would have gotten a T statistics less than 8.52. Okay? Any of the single regressors, this was the largest T ratio. Okay? Of course, find the largest correlation with Y. Okay? Taxes had the largest correlation with the actual house price. Okay. And that's it. Okay? Could I enter, then it can't remove it, obviously. Well, then the next thing you do is try to add then x1, x2, and so on, or x1. Then you've got one in. You've got taxes in. Okay, taxes is in. Okay, the model. Now you try to look at all two subset models where x1 is in the model. Okay, so that's x1, x2, x1, x3, x1, x4, and so on. Okay. Can I add the new regressor? Well, the condition is that the T statistic has to be at least 2 so that the F is at least 4. Okay? So now I can't add anything else in. Turns out. That's the end. Okay? Here we had the best alternative single variable was baths only, and the T, well, here it was. T was 4.77. Okay? So that was, so the best single variable model was x1 alone. The second best single variable model was x2 alone. Okay? And stepwise with these parameters couldn't add any more variables in. Okay? Couldn't go any further. Just died there. Okay? So it never got them removing anything because it never entered a second thing. Okay? Obviously it can't remove, if it entered at 4, it can't remove at 4 with just this one. So if I can't enter anything, can I remove it? No. Because it was already good. Alright? Alright, so now I'm going to go to F enter equals 2 and F remove equals 2, just see what happens, see if I can get some movement here. Okay, that corresponds to significance levels of about 15 to 20%. Okay, in terms of F ratios. Okay, remember the number of degrees of freedom in the denominator and the numerator will affect what those significance levels are, but it's just this kind of ballpark numbers. So sometimes computer programs use the significance level. I think I'm not sure who uses these, which program it was. Anyway, that's another mode to enter these parameters. Okay. So here, let's say, okay, taxes got entered. It was still the highest T ratio. Okay, taxes got entered. This is the first step. Okay, this is the step number. Okay, the first step, taxes got entered. It was the best single regressor. Okay, then what happened to the second step? This is a bottom line. This is a summary here. Okay, at the second step, baths got entered. Okay, why? Because the T ratio is 1.93, and if I square that, that's bigger than 2. You can see why it wasn't entered in the first step, because 1.93 squared is less than 4. So if I had put 3.5 here for f enter and f remove, then I would have gotten a 2 variable. Okay. Stepwise. Okay. 1.93 squared. Okay, it's bigger than 2. So I got BAS to come in. Now, can I take anything out? No. Well, now presumably taxes could have gone. The T ratio could have gone down. All right. It did go down. It went from 8.52 to 5.60. So you see this? The T ratio of taxes went down when I added that new one in. Okay, but it didn't go down to something so that when I squared it, it's less than 2. Right? So I don't take it out. I obviously don't take this one out because already the square was bigger than 2. So nothing got taken out. So then I could see if I could enter something else again in step 3. Well, obviously, since there is no step 3 here shown, then there was nothing else that had T ratio bigger than 1.14. After I tried all possible 3 substep models that consisted already of taxes and BAS as 2 of the variables. All right? So I'd have to do 7 regressions. Okay, if I was doing it in Excel to check. Okay, that's a lot of regressions. It's kind of straightforward pointing and clicking, but still it's a lot of mechanics and time wasted, obviously, at home. Okay, but you're going to have to play with it anyway. With the solar data, I gave you 5 variables, so it's going to be a bit of clicking. 2 to the 5th is 32 possible regressions, so you can do all possible regressions there. Just get a worksheet and don't bother looking at the residuals or anything. You just want to get the summary ANOVA tables and the coefficients, right? So just try to compactify it as much as possible. Any comments about this? So let's go to now one more case, I guess. I just said, okay, suppose I just really wanted to get selection to move around a little bit. What would I do? I could stepwise. It doesn't do that much here. Stepwise is not that interesting. It just keeps adding things in. If I put f enter as 1 and f remove as 1, it means if I got a t statistic of 1, I say, that's good enough. Let's throw it in. Okay, but then if the t statistics drop below 1, they said, no, it's not any good. Okay. So first I got taxes to go in, then I got BAS to go in was the second. Okay, we already knew that was going to happen. Okay. Then let's see what I got. I got fireplace to go in. And none of the other t statistics drop below 1, so I can't drop any of them out. Okay? Then I got, what happened here? Then I got age to come in. That is t statistic of negative 1.13, so an absolute value bigger than 1. None of the other t statistics drop below 1, so I can't drop any of them. And then I finally got garages to come in. And none of the other t statistics went below 1, so I kept it. So I just went up in a forward regression, where f in was 1. Okay? And none of them went out. I said these 3 were not significant in the end, so I would just kind of drop them from the model, and then I'd get x1, x2 again. Okay? So that's, you can play this game where you can try some different stepwise parameters, and if you consistently get the same thing every time, maybe 4, 2, and 1 are not the best choices, but it's giving you something. Okay? So it's like consistency check. See if you always get the same thing. That would be one way to do it. Let's do a look at backward elimination. I'm not doing forward here. That was equivalent to forward practically anyway, as you can see. Forward was pretty trivial. Okay? Backward elimination is a little bit more exciting. Okay? In terms of the table. Okay? Then you have, basically, f enter is 100. That's my infinity. Okay? And f remove is 1 in this example. So I start with all 9 regressors. They're all in the model. And then at step 1, what do I get? I dropped 1 out. Which one? 1, 2, 3, 4, 5, 6, 7, 8. No, I didn't have to drop anything out. This is just the full deal. This is just giving the summary that was on the very first page. It should be. This column should look exactly like the very first page in terms of the coefficients of the t statistics. Let's check that. Let's see, my coefs were, did he list them in exactly the same order too? Yeah, I think it did. So it gave me the, oh, I can't see the t-statistics. Darn it. Well, I don't need to cover that. I'll just cover it like this. Okay. Well, no, that's pretty confusing. Okay. Over on this side. Okay. Yeah, this is better. Anyway, in the same order. T-ratios were 2 point. He didn't put the constant, so it's 1.87, the 1.63, the 0.31, the 0.62, the 1.46, the negative point, and so on. Everybody with me on that? So those are exactly the same information as on the very first page. Okay? In terms of the t-statistics. Okay, now it says, okay, I'll never enter anything, but now, well, unless the t was bigger than 10. Okay, in this example. Okay, but I am going to remove. Actually, they did give you just the value of the constant. Oh, this is just the value of the constant. Didn't tell you the t ratio of the constant. Looks like. Interestingly enough. Okay, then. So, which one am I going to remove first? The lowest t, it looks like this one here, 0.17 is the smallest one. Right? So just take it out. It squares less than 1, take it out. Okay, now you've got 8 regressors, and you do the regression calculation again. Of course, you have to do it again, which is a little bit complicated with Excel, because then you have to take the column out, and then you have to close the space, okay, and then click and everything again, and so on. Okay. So think ahead a little bit how you're going to do that the most efficiently, okay, if you want to do backward elimination. Cut and paste is your key to the highway. So now what's the smallest t-statistic? Which one should I take out next? It looks like this one's the smallest one by inspection, right? So it's nice if somebody would generate this table for you, wouldn't it? But Minitab will. And then so you take it out, okay, and so on, so you can see the x's coming. And then the next, now I have 7 regressors, and I take out the smallest one, so it's trivial to see which one it's going to be. I guess it's this one here, the 0.65 is the smallest, and that's the value. So I take it out, and now I get some more t-statistics, and I still have one that's smaller than 1. It's here, okay? So I take it out. Oh no, I'm sorry, that was not the smallest one. Skipping the column. I take this one out. This is the smallest one. Living space. Take that one out, then I'm down to what? How many regressors? 1, 2, 3, 4, 5 regressors. And let's see, there's still one with the t-statistic less than 1. Okay? So I take it out, and I'm down to 1, 2, 3, 4 regressors. Okay? That gives you a model x1, x2, x5, x7. Okay? Which is the one I gave you in your homework. Okay? Or something. Test. That's what it was, a test.
And then how did you decide those two were?
Well, you can either keep them in or not keep them in. Okay, they have fairly large t-statistics still, 1.7, you know. It's not that small. The p-values would be, 10%. You might keep them or you might not. It's up to you. Okay?
So is this cooked up data?
No.
It's done?
This is data that was in the book.
Yeah, I know. I just wonder if they cooked it up.
Well, as you can see, it's really old. We're talking about houses that are between $30,000 and $45,000. They had 3 bedrooms and 2 baths, or 4 bedrooms and 2 baths, or 1.5 baths, I guess was what it was. This was the good old days when you could get a house for $40,000. So it's a good old days. So I don't know when it's from. Maybe the early 70s or something.
I just never would have considered taxes and that. Because isn't that basically saying that that's what you're basing your price on?
Yeah.
In the overall.
Yeah, and you did some influence analysis too, which you can really get into if you want to. There were a couple points in the data that said it didn't seem to fit some of the other ones. Like it was a newer house or something like that, and it had, it's almost like it didn't fit in the data set. It went for a higher price, yet it had smaller number of baths, and it only had 1 bath, something like that, and 3 bedrooms instead of 4 bedrooms. Okay, but maybe it had 2 garages or garage stalls or something like that. I don't know. And it went for the higher price, but that was one of those that had a large had a large residual or something. So you could kind of play with it. But in terms of, realistic today, I'm sure it's changed a little bit. Okay. Okay. Taxes was the most important variable back then. I guess the assessor was doing that job. Okay. Comments or questions about this? So, which is the best one? X1, X2 is a good choice. X1, X2, X5 alone is probably not a great choice, but it's still not that bad. X1, X2, X5, X7, is another possibility. If you want four regressors. If you want to keep it simple, X1 and X2. Okay? I didn't look at the minimum. I forgot to look at the minimum mean square for error on there. I guess we could just look at it, eyeball that. What we did see was R square. We did look at the R square and minimum S. The minimum S was at let's see, X1, X2, X5, X7. Among these possible models, it was at 2.68 was the minimum S. Let's see, what was which is the square root of sigma squared, 2.68. I didn't get down to the X1, X2 model. What was the X1, X2 model S? Did we calculate it? The square root of 7.80. What is that? I'd have to calculate it. Did not show. Oh yeah, 2.792. So actually, it did show that the minimum. So X1, X2, X5, X7 probably competes for the minimum MS Res P. Okay. So I think in the text somewhere it says that you consider the MS Res P and the CPs is two possible measures for what's best. So the minimum CP. So you consider the two. If you get consistency in both of those criteria, then you say that's the best model. So you consider minimum CP and minimum MS Res P. Those are the criteria. And I believe that this one came out to be the X1, X2 model. Okay, and this one came out to be X1, X2, X5, X7. I believe. Okay? In those cases. For the house data. I didn't absolutely check that because I didn't do all possible regressions to see if there was a smaller MS Res P. But my guess is this was correct. So I'm not absolutely certain. But it certainly, it came out as a backward elimination model and it certainly competes for a small MS Res. Okay, MS Res P here is not that much smaller than here, though. Okay, I think what did you get? You got sigma hat was equal to. In this problem, it was 2.68. Here's sigma hat. I'm sorry, MS Res P square root equals 2.68, and MS Res P here, with P, this was of course P equals to 3, and this is with P equals to 5, but still that's how you're going to compare them. Okay, this came out to be for X1, X2 it was let's say calculated as 2.792. Okay. This had CP equal to 0.826, and this had CP equal to. Did I actually calculate CP in this case? I believe I did, but it's not on these pages. I have to find it in my notes somewhere. Okay, I didn't actually calculate CP there. I had all these slides. Okay. I did calculate it somewhere along the line.
You did the 125.
125, yeah, and 1257. I didn't calculate the CP there on the page. Okay. It's somewhere in my notes, but I can't seem to find it right now. Okay. Why don't we go on? And let's talk a little bit about the CP. I just wanted, that's the end of the last notes, notes number 11. I wanted to go back and actually derive what CP is.
The F enter and F remove, are those something that you pick?
Yes, you pick them.
Formula?
Yes, there's no formula for them. You just pick them. You pick them. And the author mentioned, you could pick some and then, or you could actually kind of tune, if you were doing a lot of regressions, you could kind of tune your system and to whatever kind of data you're working with those. If you're working with a lot of similar types of data or something like that. But I think the better way is to try a couple, like I did, I tried 3 different scenarios. Take n equals f remove and keep them equal, maybe do 4, 3, and 2, and just sort of see what you get, right, with stepwise. And if you get consistent information, then that's your best model. Try a backward elimination, try a forward as well. Directed search on T if you want. Those are all easy things to do. So you just try a few and see what you get. And of course, you do all possible regressions and find the minimum CP and minimum MS-Res P. So you look at those as also candidates for a best model and see what kind of consistency you get. If 9 times out of 10 you come up with one model, you say, okay, that's probably it. You just use the majority vote rule in terms of you try, you get 10 scenarios, and if 9 out of 10, if you get 10 results, and if 9 out of 10 of them were one model, then you just choose that. Okay, that's the good case, right? If you got 40% of the time one model, 40% another model, and 30% yet a third model, maybe they're all pretty decent. Just see how much they overlap then. Okay, what's the intersection of the subsets? Is that anything good? Okay, that's the core then. All right, if they're totally disjoint, then you have a problem. Okay, that doesn't seem too likely. Or then you check for multicollinearity, obviously. You say, oh, okay, these variables are really, telling you the same thing. All right, what about that? How do I deal with that? So, in practice, if you go out there and do it, it should be kind of fun, huh? Okay. Well, find out if it does. I'm sure it does these days. With the price of land going up, people are just buying the land and raising the house. Right? I mean, they call it dozing, right? Yeah. And they're just using it as just land there and sitting there. They don't have to pay any taxes on it anymore, hardly, because there's no improvements. So then they just wait until it's worth a lot of money. They sell it to the appropriate developer. Yeah, or do something like that. There's lots of people doing that, but anyway, I'm sure land is worth something now. Yeah, it all depends where you are. So very, very much in context. Yeah. So what is the CP statistic? Let's look at that a little bit. One last time for just a little dash of theory. Okay. It's called Mallow's CP statistic. Okay. What am I trying to do? I'm trying to introduce, I think I mentioned the total mean square error is, maybe I didn't write very good notes here. is the summation. Let me see what I have here. Yeah. What I want to do is I want to calculate so the total mean square error. Oh, I call it total standardized. Total mean square error is this. Total mean square error is summation. It's EYI minus YI hat. And I'll put a P here, okay, for a subset model, P, okay. Squared here, underneath the expectation sign, I goes from 1 to n. Okay, total mean square error for a subset model, P. I don't actually say what for a P subset model. I don't say what subset it is. I'm not going to add that into the notation. But basically, you predict the ith y value using a P subset model. Okay, so you do the regression on P columns for the X matrix. You get the corresponding coefficients. You actually predict Y. Okay, and that's your Y hat I comma P. All right, he didn't even put the P in there in his page 299. He should have. Okay, because really the YI hat depends on P. How many regressors you have in the model, right? It's not just independent of that. So that's the total mean square error, and then you normalize it by dividing by sigma squared. That's all he's got here. But he doesn't quite do that. So then he defines gamma sub P equals 1 over sigma squared times this thing. Summation I goes from 1 to n E yi minus yip hat squared. So it's exactly the same thing, only divided by sigma squared, just normalized. By sigma squared. Okay? By division by sigma squared. Okay, so that's what the gamma sub P is. He does have the P in there finally. Okay? Because it doesn't look like there should be any P in there if you just look at 913. Okay? Now 913 is actually written is slightly different. Because what are you doing? What you're doing is you know the rule for the expectation of a square. Right? What is the expectation of a square? Remember that? I've done this many a time. The shortcut formula for the variance is expectation of the square minus the square of the expectation. So turning that around, you get expectation of a square, W squared, is equal to the expectation of W, the quantity squared, plus the variance of W. Okay? It's the basic identity that we use here. So if I take this and use that identity there, okay, and put in here, that's the W squared, right? So we get E of W, so that's equal to 1 over sigma squared then, summation, I goes from 1 to n. And now I'm going to use that formula in each of the n summands, and I get, what? Expectation of yi minus expectation yip hat, okay, squared, plus variance of what am I doing here? Oh, I see. He's got something tricky. Oh, I see what he's done. Oh, I'm sorry. This is not correct. He wants EYI. He wants EYI here. So this is a little bit different. So there's another E in here. I see. Yeah, so this is the expected response, and this is how well this is total mean square error for a P sub. This is what he's actually going to compute. Okay? He's not actually going to put the YI in here. because what that would be the expectation of SS res P. This is a little bit different. Okay? Yeah. Yeah. Maybe I got something wrong here. But this is what it's got here in the top of page. This is 912. From 912. Okay, this is correct. I want to get this correct. So I have the EYI in here, which is simply X beta, where X is the full model. Okay? At the ith place. So this is the definition. This is a definition. Okay. Make sure you got this right.
So is this extra E here? It's not. It shouldn't be up there.
He's got the extra E in 912. This is what I'm following. Okay? Morrow says produce a criterion is related to the mean square error of a fitted value. Mean square error of a fitted value. This is the mean square error of a fitted value. This is what you're trying to estimate. This is what you're trying to estimate. Yi p hat is trying to estimate EYI. So this is the mean square error of a fitted value. This is correct. The other one was not a mean square error of a fitted value. Mean square error, you're always taking the variable minus what you're trying to estimate. Okay? It's theta hat this is your theta hat minus your theta. You're trying to estimate this with this. Okay? So this is a mean square error MSE of a theta hat is always equal to expectation of theta minus theta hat squared. But theta is a constant. Okay, here I had the yi, which is not a constant. So that looks like an error in the notes. I didn't write it down actually in my notes. So this definition. So I want to make this clear. Total mean square error for a P subset model. Okay? So he didn't actually write this definition down. Okay? Skip that step. So I want to make sure that that's in there. But it makes sense. This whole expectation is the mean square error. Alright? So he's got his theta written as an EYI. Okay? That's the mean square error of a single fitted value. Now take the sum of all those and you get the total mean square error. Now, so now I'm going to define this by normalizing that, just by dividing by sigma squared. Now, what is that? That's this plus what is the, so this is your expectation of theta minus theta hat, so that's theta minus E theta hat. Right? Well, this comes out, this is your theta minus your E theta hat here. Okay, so that's actually your bias. Right? It's a bias. And you square that. Okay? Plus, what's the variance of this? See, this was a difference of two variables before, and I didn't want that. That's why I caught myself. What's the variance of this? Well, the variance, that's a constant. Theta, all right? So that doesn't come into the variability. Only this term does. So this is plus the variance of YIP hat. Okay? So that's what it is. Now I can calculate the variance of YIP hat, sum on all n. Okay? What is it? The variance, what is y hat sub p is equal to x sub p prime x sub p inverse x sub p y. Okay, well that's the hat matrix for the P subset model. All right? This is the hat matrix for a P subset model. So you're just taking P columns for X. It's just the intercept and the P minus 1 regressors, if that's what you have. Okay. And so what is the variance of that? The variance of Y sub P hat, then, the variance, remember our handy dandy formula for the variance of a random vector? was take this, if I call that h sub p y, all right, then that simply is h sub p, the variance of y, times h sub p prime. But h sub p is symmetric, and variance of y is sigma squared times the identity. So this is sigma squared times the identity times h sub p prime. But h is a hat matrix, meaning that I squared is the same, and it's symmetric, so you get sigma squared times h sub p. Okay. So now, the variances of the sum of the variances of all the yi's, all right? That's an n by n matrix, by the way. This is an n by n matrix, and along the diagonal you get the variances of the yi hats. Along the off diagonals, you get off the main diagonal, you get covariance yi hat, yj hat. Okay. So this is the full variance covariance matrix of the full n by 1 vector, random vector. Okay. So that's a n by n matrix. Now I want this sum is just the sum of the diagonal elements. So I want to get the sum of the diagonal elements of that matrix. What's that equal to? What's the sum of the diagonal elements of sigma squared times that H matrix? Well, here's the H matrix. The sum of the diagonal is sigma squared times the sum of the diagonal entries of this. That sum of the diagonal entries is the trace. So this is equal to 1 over sigma squared. This is what we're calling SSBP. Okay. Times SSBP. The sum of the squares of the biases in the fit. Okay? B for bias. Because this is the bias in estimating yi hat p. Estimating the EYI by yi hat p. You take the difference of the parameter and the expectation of the estimator. That's the bias. Okay? So this is the sum of the squares of the biases. Just add them all up. Okay? And that's SSBP. Plus 1 over sigma squared times the trace of this H sub P. Okay? The 1 over sigma squared just come in from this definition here. And that's the variance term. So those are the two terms. Okay? But what is the trace of this hat matrix? Remember how that goes? The trace of, remember the other handy dandy formula we had for calculating traces was a trace of a product, ABC, trace of ABC is equal to the trace of CAB. Okay? As long as all the products make sense. As long as I can permute the C in front of the A, all right, and still have a valid matrix product. This might be an n by n matrix. This might be a p by p matrix. Okay, and that's the way it works. In fact, this is an n by n matrix. Okay, and then when I put the xp, sorry, there should have been an xp prime here. When I put the xp prime in front here, now I have a p by p matrix, and it's actually the p by p identity matrix. So then, this is my HP, right? I put this xp prime in front, I get the identity matrix. So I get the trace of xp, xp, prime xp inverse, xp prime, equal to the trace, that's an n by n matrix, equal to the trace of an xp prime xp times xp prime xp inverse. Obviously, since it's invertible, then I just get the identity there, which is the trace of the identity, which is equal to p. Sum of the ones along the p by p identity matrix is equal to p. So this is giving you a sigma squared times p. So I get 1 over sigma squared SSBP plus 1 over sigma squared times p sigma squared. Those cancel, and I get plus p. Better be. Okay? Okay. Equals 1 over sigma squared SSBP plus p. Okay, so that's one identity. That is gamma p, which is just this normalized total mean square error for a p subset model. That's what I want, and I want to get that to be small. Okay?
I would like the gamma p to be small. How am I going to do that? Okay? That's one thing. Well, that'll be by somehow keeping p small and also keeping this one. There's two contributors, right? The p and this SSBP. Okay? So I want to look at the SSBP. Can I have an identity for that? Well, let's look at expectation of SS res p on the other hand. Okay, so now that I can erase this definition, I think, or I can erase something. Maybe I can just put it over in this little corner. We're done with this little corner here. Okay, so now I want to say something else. What is SS res p? SS res p, remember, is actually the thing that is defined to be what I had before, okay, without the expectation, okay? SS res p, on the other hand, is expectation, well, ESS res p, I can calculate. ESS res p, on the other hand, is the expectation of, here I just put a double bold E so it's easier to read, of summation I goes from 1 to n, yi minus yip hat squared. Okay? Because that is the definition of the residual. Now, what do I have for an identity for that? This is now here's what I was going to. This is by the same type of identity that I had before. This is SSBP. Okay, I don't have the division by sigma squared here, so I keep in the sigma squared is going to come out in the wash in here. But this is plus. Let's see. I'm just using the fact that if I take the expectation of this squared, using this identity again over here. Now I get, indeed, the sum of the squares of the biases plus the variance not of just yip hat, but now of yi minus yip hat. This is where I was going to start before, and I stopped myself because this is the right place to put it. It's in the definition of the SS res p. And then now I need, so there's the expectation of the square, which is the square of the expectation, which is, after summing on I, is going to be this bias term, plus the variance of, now it's the difference of two variables. Now I have to go ahead and calculate the variance of y minus y hat p. But that's not difficult either, because now the variance covariance matrix of y minus y hat p is the variance of I minus h sub p y. And now use the handy-dandy formula again. And you get I minus h sub p times sigma squared I, so n in this case, this is n by n identity matrix, times for the variance of y, that was assuming that we had independent and constant variance y's, times I minus h sub p prime again, and now h is equal to hp prime, and multiply I minus hp squared, and you get I minus hp. So this comes out to be sigma squared I minus hp. You get I minus 2h plus h squared. H squared is equal to h, so I minus 2h plus h, I minus h. Period. Okay? So that's that one. So now if I want to take this, I can take the trace of the I minus h. Right? So this equals SSBP plus the trace plus sigma squared times the trace of I minus h sub p. We just calculated, and this is the n by n identity matrix. And that's an n by n hat matrix. Okay, so everything makes sense there. We just calculated the trace of a difference is obviously the difference of traces. And so you just get n minus p here. So this is equal to SSBP plus sigma squared times n minus p. Okay.
And that's an identity for the expectation of SS res P. So we expect SS res P to be about this without the expectation sign. Okay. Now what do you do then? How do you put these two identities together? Okay. So what I'm going to do is first rewrite the identity for gamma P using this identity as a substitution. Right? What I can do is substitute this, and I can rewrite gamma P. I guess it's not very difficult to do. Rewrite gamma P. So if I call this 1 and this 2, equation 2, I sub equation 2 into equation 1, and I rewrite by subbing, is that a word? Substituting 2 into 1, and somehow doing the algebraic manipulations, right? And you get the following formula. Then you get, I think everybody can believe me, gamma P, without actually showing that I can't do the algebra, is, let's see. I guess I could divide both sides by sigma squared. How's that? Okay? And so I get an n minus p plus s. I could get this term, so I'd get I'd solve for SSBP in the equation 2, right? Or SSBP over sigma squared, and so I'd get SSBP over sigma squared plus p is equal to ESS res p over sigma squared. Okay. Okay. Minus n minus p plus p. Okay? That's an identity then. Where sigma squared is the full model variance. So there's no hat on there or anything. That's just it. Okay? Which is ESS res P over sigma squared minus n plus 2p. Okay, so that's your gamma p. Remember I said I wanted to make this thing small? So I want this to be small. Okay, gamma p small. What is CP? CP is a data-driven version of gamma p. Gamma p is something that I can't actually calculate because there's an expectation sign here. Okay. So what do I do is instead of this, I put down the data version of it. In other words, I take sigma squared and replace it by sigma hat squared, and I take the e off this. You just take the e's away, right? Because this is e of sigma hat squared downstairs. Because sigma hat squared under the full model really is unbiased. Sigma hat squared is unbiased for sigma squared in the full model. Okay, so now all I do is to get CP, I take this is gamma p, which is a theoretical expression. Now to get CP, I just take the e's away, and then that's Mallow's CP statistic, standard thing to do. Okay, so I want to make it small. Get small mean square error for the fit. So X1, X2 model fits the best in some sense. Questions about this? Okay, so CP, take away the E. CP equals. So it leaves a half a page of the book to do it, but CP is equal to SS res P. Hopefully you understand what the heck it is. I can test you on that, right? You know, maybe not this derivation, though that would be key. I guess that would be fair for the graduate students. But at least on what the heck it is. Okay? It's probably going to be more applied, but I have to find something for the graduate students to chew on. So let me see. I'll come up with some ideas by next time, I guess, if there's going to be any refinements. Okay? I said you said you needed to leave at 12:15, so why don't we take a break here? Okay?